All right, trig identities. So there are three groups of trig identities that the book talks about. The first is these Pythagorean, and they call them Pythagorean identities because they are based upon the Pythagorean. And the proof of any of these, deriving any of these, you use the Pythagorean. You basically just, the best way is to, or better yet, memorize that you need to look the damn things up, because I don't really remember. The only one I remember always is sine squared plus cosine, and that's a good one. Or the other ones are secant squared minus tangent squared equals 1. Another. And then cosecant squared minus cotangent. So I don't know. I don't really like the way they have these set up. This is the way the book writes them. I prefer them like this. Secant squared theta, oops, pardon me, minus tangent squared theta equals 1. Likewise, cosecant squared theta minus cotangent squared theta also equals. Yeah. So I guess the way to, if you were going to try to memorize these, the two cos go together. The only one that's a plus is the sine and the cosine. All right. If you're gonna memorize them, the only one that's a plus is the one that relates sine and cosine. So sine plus cosine equals 1. Then the other two are both differences. So it's a minus, and it's the secants minus the tangents. All right. And the cos go together. Cosecant squared minus cotangent squared equals 1. Secant squared minus tangent. And you can rearrange them. I don't know, yoga. Yeah, this is how the book writes them, but this, to me, this is an easier way. The Pythagorean formulas. So, who wants to earn some house points? Anyone? You? Good. Cool. Prove the first one. Prove! Oh, no, oh my God. Want to try? No. No, that's just the identity. How can you prove it? You want to try? You want to take a stab at it? Who wants to take a stab at it?
Go ahead.
It can be a team effort.
Wait, does it have to do? I don't actually agree. I'm guessing. Ashley, go.
No, I said you want.
Okay. So does it? Does it have to do what sine equals?
Yeah, sure. That's a great way to think about it. Yeah. So what is sine?
Sine. So opposite over.
I switch
Nice.
it to a blank screen.
Now Lynch just goes, and Yes, I got it, Ashley.
Negative.
And then,
That's right. Those are right.
okay, so how does it work?
How would you prove that sine squared plus cosine squared equals? No, y over r plus x over r does not equal 1. Establish that, right? Y over r does not equal sine squared. Y over r equals sine, right? So it's y squared over r squared.
So,
Here,
we,
let's give you a whole screen to do it.
Cool.
So let's write it down. This is sine squared theta plus cosine squared. And we established that sine equals y over x, no, y over r, and cosine equals x over r. There you go. All right. Have at it.
Okay. Pythagorean.
Say that again.
no, art. You mean, like, word?
That's right. That's right.
What?
So that
No.
r squared times.
Okay.
Yay! You did it. That's it.
Woo!
Yeah, that's it.
I didn't do it. I didn't do it.
That's it.
I turned the 1 into an R.
Do you see how you did it?
No.
Okay. Walk
Maybe
her
if I
through
was-
it more slowly.
Wait, no. If I'm sitting over there, I'll probably.
Walk her through it more slowly. Yeah.
Now, hold on. You can get rid of the denominator.
Yes. Right.
So you'd have to multiply r squared over 1.
Right.
Is that? Oh, you want to just multiply both sides
Yes.
by r squared. Yeah. So we're going to multiply this side by r squared
Yes.
and 1 times squared.
But it's still equal.
Right.
So then the r squared over 1 is just cross the cancel.
Yeah.
Right. Numerator. Squared.
Yeah. That's
Yeah.
that's
You
beautiful.
can say no.
But why is
That's the Pythagorean, and we know that that is. Okay. So yeah, we're gonna we're going to give Lance. We'll give Lance 5. Mars will give you 3 for having the moxie to get up there, and Ash 5. Is that right? Okay. How about 4?
Hey.
How about 4?
How about you?
No.
Mar's like, no. You're like, oh.
No, then it gets too meta.
Okay. Yeah, so this is the way I did it. It's essentially the same thing. We know that this and this is, y squared over r, y squared over r squared plus x squared over r squared gives us that. And then from the Pythagorean theorem, we know that this equals r squared, which brings us to 1 equals 1. You follow that? It's kind of the same thing, but I did.
I understand the whole thing. Did you get?
I took y squared plus x squared, rather than doing what she did, which was to just multiply both sides by r squared and get r squared equals, which is the Pythagorean theorem. I took from the Pythagorean theorem that y squared plus x squared equals r squared, and I just took r squared and I plugged it in for y squared plus x squared. So I got r squared over r squared equals 1. So we know 1 equals. Does that make sense? It's essentially the same thing. Okay. So if you would get out your laptops, and go to the Desmos. There's the link in the class website that I have there. Or the link is on the Google Classroom, or you can just Google Desmos. All right. Yeah. So I want to let's see what I was planning on here. I don't really remember. Yeah, you can Google it, or it's in the classroom. Bookmark it if you want. So when you're in here, I'd like you to go into graph settings and click Radians. Yeah, and just make sure that it's on Radians. It should be. Yeah. Okay. Now I'd like you to type in sine x. Oops. Okay. So this is showing you for all values of theta what the sine value is. What do you notice about that? How would you describe that? Yeah, it's a wavy line. It's a wavy line. How else can you describe it? What are other? Okay, so I'm imagining a wavy line. Pretend I'm blind. You're telling me to visualize something.
It can go negative infinity and positive.
Negative infinity, what? On the x-axis or
Yes.
y? Okay. More than one.
The
Can't
high,
be more
the
than
high
one.
is
Minimum.
minimum is
Okay, good, good, good. I like it. Yeah. What about the origin? Start. Okay. Another thing that you may be able to notice here is that what is you've given me almost everything, right?
It starts.
It starts at 0, so the origin is at 0, 0. And the last thing here, so you've given me the amplitude, which is 1 to and the last thing is the wave. It's 2 pi. So this would be pi, or 180 degrees, and this would be 2 pi. All right, so that's the sine function. Next, I would like you to hit the little plus sign here. Or just click into the number 2. And let's type in sine and then squared of x. I did squared by hitting shift and caret top. Yeah, the caret. It's above 6. Yeah.
Oh.
Shift.
Oh.
Okay. And
Now how do you
so,
get-
what do you notice now? Oh. Okay. Now, this should have drawn something for you. What do you see? It's not the same. The wavelength. The frequency is the inverse of the wavelength. Yeah. Peak to peak is the wavelength. The periodicity. Yeah. So, again, now, describe for me, what do we see different? Really, what's different in these? What's the same? They're both wave, right? Yeah. It doesn't go into the negative. Why? Its minimum is 0, but why is the minimum 0? Squares, no numbers, except an imaginary. Yeah. Sine starts at 0.
You know how this blue line. It's not like. And what
Right.
he said-
Yeah. One of the things you can think of as what it did here is it just took these bottom parts of the wave and kind of flipped them up. It's like you took the absolute values, right? It's not exactly that. Yeah. You see what happened? So don't. It's not the sine squared curve is not the sine curve. It's similar to. So don't be misled. Okay, so the next thing we're going to do, let's click onto 3 and do cosine of x. Yeah, all right. And if you want, if it's getting too crazy for your eyes there, you can just X out the sine squared if you wish, or you can leave it if you're fine. So how would you compare the sine curve to the cosine? They do. They start at different points. Sure. So that's something that's different about them. What exactly? How would you describe them starting at? Yeah. No. What were you? You had some other thing. They have the same amplitude. They have the same amplitude. What about the wavelength? It's the same. They're just offset. Their offset, it's not quite by pi. No, because if this is pi right here, right? So if I were to take this curve and move it back by pi, the blue would be going up here and down here like this. So for example, let's see here. Minus. Let's see if I can do it like this. Minus pi over 2. Oops, no. Oops. Oops, no. Cosine x minus pi over 2. There we go. Oops, no. Plus. There we are. So you can see if it was this is what it would look like if it was offset by pi. It's not. It's offset by pi over 2. Does that make 90? Because if that should make sense if you remember what we were doing out there. As sine was climbing in value up to 90 degrees, cosine was falling in value up. So sine started at 0 and went up to 1. Or it started at 0 and went up to 1, whereas cosine started at 1 and went up to we got through the 90 pi. Who does not understand? Everyone? Sort of? No?
Yeah.
Okay. Okay. Well, I won't say it again then. So then let's do cosine squared. Cosine squared of x. Look at that. Geez, it's starting to look crazy, isn't it? So again, offset by 90 degrees. Offset by pi over 2 from. So it would be the same curve if you shifted it along the x-axis by pi over 2, by 9. No? Okay, so let me, should I do it in sine and cosine, or sine squared and cosine squared? Yeah, let's just do it sine and, okay, let's just do this. Is that big enough for you? Okay, should I make it bigger? All right. So the red is sine, right? And let's imagine this here is our quadrant. And so to start off, we have this triangle. Here's the right angle. And sine is y over r, and cosine is x over r. So at this small angle, which is this, theta, here we are at theta at a small angle, the y value is very small, and the r value is pretty big. All right, so a small value divided by a big value is going to be a small positive value for r. Whereas for x, here's the x value, which is pretty similar to the r value, so it's going to be close to 1. All right, and as we take these different triangles that we've made, the sine value climbs up until we get to 90 degrees, or pi over 2, right? We get to this point, and y is essentially equal to r right up here at 90 degrees, whereas x is 0, right? So the cosine value has dropped down to 0, whereas the sine value has climbed up to 1. And if we keep going into this quadrant, sine's going to come back down towards 0, and because these x values are negative, our cosine is going to drop into the negative territory. Right? So we have these two waves that are going along the x-axis, and they're similar to one another, but one is just shifted. It's shifted by 90 degrees. If you measure this distance right here, that is pi over 2, or 90 degrees in distance. So if you were to add, imagine adding pi over 2 to the cosine, you would get to the sine. It would just shift that curve over to be the sine value. Does that make sense? No, it doesn't.
I understand that.
Okay. Yeah, the triangles, that's what we were doing outside. Yeah. And so, that's all that we're doing. We're looking, the sine, remember, is just defined. We define sine as the ratio of the y value in a triangle over the r, the hypotenuse. And the cosine is just the x over the r. And so as you're sweeping out this angle, theta, the y value starts small and moves up to the point where it equals the r, and the x value, which starts out equal to the r, or that ratio being 1, and it moves down to 0. Does that make sense? Yeah. And then when we when we keep extending theta into the second quadrant, or whatever quadrant, as we extend into the next quadrant, cosine is based on the x values. Those x values are negative. They're negative. So it's a negative value. The x is a small negative value, and r is the same as it always is. So, the triangle would be like this. This r value is a small negative divided by a large positive number, and so you're going to get a small negative number. And you're going to continue until you get down to here, which is this triangle, where x is a negative number that's equal to the r. No?
You can move on.
Okay. Yeah, I mean, this is what we were trying to do out there. But the idea is that r is So r is the same as it sweeps around the whole circle, right? X is positive, small, X is large positive, large, smaller, 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 small, 0, small negative, bigger, 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 equal to R, negative though, and then also equal to R negative, staying negative but getting smaller, smaller, smaller. Now X is 0, and now X is going to become positive and small, right? This X value, and X value is now equal to R. I'm right here. So that's the cosine. Let's move this over. Oops. Right here, cosine is 1 because X is equal to R. And then X is now 0. X is negative and small, getting bigger. X is negative but equal to R. Comes around. X is getting smaller till X is 0. Still negative, but 0. X is positive, smaller, getting bigger. Now X is equal to R. Okay? And likewise, for Y. Y is 0 right here. 0 over R. Y is getting bigger. It's positive. Y is equal to R. Y is getting smaller, still positive. Now Y is 0. This Y value along the Y axis. Now Y is negative. All the way down to Y is equal to R. Y is getting smaller, negative, up until it becomes 0 again. All right. So if you look at what's going on here, these two curves are just shifted from one another by pi over 2. Right? They're the same curve. It's just one is shifted along the x-axis by pi over 2, or 90 degrees. They're 90 degrees, what's called out of phase. Does that make sense? Did that give it to you a little bit better? Okay, so let's try this next thing. Let's try sine squared x. Let's put that in parentheses. Plus cosine squared x. What happened? What's that? It's a straight line. Why? What the hell happened?
Because it equals 1.
Sine squared plus cosine equals 1. Right. Right. Yeah. So let's put sine squared back on there. Sine squared of x. And then let's put cosine squared of x on there. Cosine. Oops. Oops. Cosine squared of x. All right. And let's just get rid of the sine and the cosine. We don't need that on there. So we can see graphically how sine squared plus cosine squared equals 1. Right? If we're going to add the red and the green to one another, if you're going to add the red, which is what we're doing, it's going to add up to the black line, won't it? If you add whatever value the green is at to whatever value the red is at, it's going to be 1. Does that you guys see how that works? All right. So I had done this. But I kind of already gave you the answer. So the house points, I don't know how compelling these house points are going to be. I was saying, how about this now? Cosine x plus sine x, what? Fill in the blank, equals 0. Want those points? No? So here's an expression. I give you this expression that the cosine of x, I've already shown you how the sine squared and cosine squared equals 1, right? We saw it graphically. I'm saying cosine x plus sine of x what plus or minus what equals 0. So let's...
minus.
It's unlikely to be minus 1. What are you going to add to theta or subtract from theta to get it so that this is... so let's see here. Let me put... Yeah. That's it, Lance. Go get it, boy. What is it? So let's see here. We've got cosine x. Let's get rid of these. We've got cosine x, sine x. What are we going to do? What if we want to get this such that if we added this, the black curve to the purple curve, what are we going to add or subtract to theta so that the two of them always equal 0? You see what I'm saying? You're on the right path. I'm not saying you got it yet, but let's think about it. Let's make it bigger here. So what does the sine have to be to add to the cosine for it to be 0 right here at this thing? What are you going to add to plus 1? Minus 1. Okay, yeah. Right. That's what we want the sine of x, the sine of whatever's in there to be equal to. But you can't just add 1, right? We're in radians. We want the sine of whatever to be equal to minus 1. Yeah, and how do we get that? So x right here is 0, but sine of 0 is not minus 1. Sine of 0 is 0, right? So we need sine of 0 plus or minus something that will get us return a sine value of negative 1, which is over here. Huh? That's at minus pi over 2. So what we want is we want the sine of whatever's in here to equal minus 1. The sine of x, we'll say plus or minus some amount. We'll just say plus. Equals minus 1. We know x equals 0. Sine of 0 plus what equals minus 1. So this is negative pi over 2 right there. You guys follow that? Yeah. So sine of 0 plus a negative pi over 2 is going to give us minus 1. So in general, the sine of x minus pi over 2 is going to give us 0 when added to the cosine of x. follow what I did? Does that work? Can you type it in?
Yeah, can you just?
Yeah.
I'm just confused about what we're like.
Yeah, we're trying to figure out what you would have to add or subtract to the x value to get it so that it's in phase, or not in phase, but like opposite phase to the cosine, so that the two of them cancel out to get. Yep. In phase means they're like identical graph. Out of phase means they cancel one. And so I was trying to get it out of phase. And let's type it in. So cosine, cosine of x. Geez, what am I doing here? Cosine of x plus the sine of x minus pi over 2. Oops. Okay. Here it is. It's just all right. You want to, let's look, before we do that, let's just get rid of the cosine of x. Let's get rid of the cosine of x. So I just took the sine curve and I shifted it by 90 degrees, or pi over 2. Are you guys all right?
Yeah,
Farting on each other? Everybody with me? Okay. Okay. So let's go back to class here. Yeah, minus pi over 2. So I have a graphical representation that maybe will help with that. I don't know, maybe it won't. But here's sine, here's the sine value. Here is y, here's x, right? And this is what the sine value would look like. And sine squared is like this. It creates a surface that's like the bubble, like a egg container. If you look at sine squared, which is in yellow, and it's out of phase by 90 degrees from the cosine squared of x, it has this blue shape. If you add the two of them together, you get this like flat, which equals, I don't know, maybe that depiction doesn't help you, but I was trying to show a different way of looking at it. All right, on to the next identities, these quotient identities. So for all angles, any angles in which the denominators aren't 0, so that means any angles for which the denominators are defined, these identities hold true. So sine over cosine equals tangent, and the inverse of that, the cosine over the sine equals the cotangent. So those are the quotient identity. And let's see if we can prove that. So sine, does anyone else want to go for some house points and do it, or you guys want to watch me prove? You want to try? Do it. Get some points. Yeah.
Cosine.
Yeah. Yep. Yep. Pretty straightforward. Give you 5 for that. All right. And the same thing is going to hold here. It's just going to be reversed. And we know that cotangent is x over y. How are you going to remember that? Well, why would you ever divide sine by tan? Huh? What is that photo? Your dog, yeah. Why would you ever divide sine by tan? Just cause. Maybe that'll help you. Yeah, maybe that'll help you remember it. Okay, so that was a joke, but it's true. It'll help you remember the quotient identities. Another one here is sine over cosine equals tangerine. These are just for her.
Tangerine. That's so funny. Why is nobody else laughing?
Sine over cosine. All right. Why doesn't a trigonometrician gotta go to the beach? Go to the beach. Why doesn't a trigonometrician go to the beach? You guys ready for this one? Because she knows she only needs sine and cosine to get a tan. Yeah. All right. The quotient identities. Are they in there now? Sine over cosine equals tangerine. Yeah. Okay. The third group of them is this reciprocal identity. So these are all pretty straightforward. For any angle, there's just, it's inverse. So the sine is y over r, and cosecant is r over y, etc. Cosine is x over r, secant is r over x, and then tangent and cotangent are just the reciprocals of one. Those are all the trigonometric identities. There's the Pythagorean ones, which are, you guys remember them? You want me to, what's the Pythagorean identities? Yeah. What are the others? There's 2 others. Yeah. The other way I did that was I wrote it as secant minus tan equals 1, and then cosecant squared minus cotangent squared equals 1. Okay. I think, yeah, great. So then let's, all right. Determine the signs of the trigonometric functions of the angle and standard position of the given measure. Okay. So sine, cosine, tangent, cosecant, secant, and cotangent. So sine is y over r, x over r, y over x, and cosecant is r over y, secant is r over x, and cotangent is x. And minus 80 is down here somewhere. So our x is positive, y equals negative, and r is always going to be. So y over r is going to be negative. Cosine x over r is positive. Am I going too fast?
No, I thought I was asking. Like, yeah, I didn't. Like, what's sine of it? What's cosine of it? Yeah, that's really.
No, it doesn't want to know. It just wants to know the sign.
I got that.
So okay, you didn't need this one done. Okay. What's the next one? Eight. 58. Yeah, sure. Determine whether each statement is possible or impossible. Cotangent of theta is 0.93. Okay, so cotangent is x over y. And is it possible to have an x that is positive and a y that is positive? Yes. Where the x is less than the y. So that's going to be somewhere in this. So the x needs to be less than the y. So x less than the y, it's going to be greater than, in fact, I can give you a range. So theta must, and it's not asking for this, but yeah, 45 degrees must be less than or equal to theta, which is less than or equal to 90 degrees. It's somewhere in. It's not asking for that level, but yes, it is. In fact, you could give a boundary. Yeah. Is that the one? Another one I picked out? Yeah. Well, we know. So what is sine? Sine is y over r. Yeah. So they have those boundary rules, but those boundary rules. Yeah, and we saw that, right? We watched the sine. We looked at the sine curve, and you were like, "Oh, it never gets larger than 1 or greater than -1 or less than -1." Right? Yeah. The thing. Oh, okay. So in cotangent, how did I do that? I guess I just. Tangent is all real numbers. Cotangent is also going to be all real numbers. I mean, essentially pretty much any value. Yeah, I mean, there's going to be like multiples of pi where it's undefined, but. All right. Next, anything else? 65. It's another one of these? No. Okay. Use the identities to solve each of the following. Rationalize the denominators when applicable. Find cosine theta, given that sine is 3 over 5. So we know it's in quadrant 2. It's over here. And that r equals 5, y equals 3. And theta is over here. So that means that yeah, let's do that. It's a great idea. So 25 equals 9 plus 16, so x equals 4. And we know it's over here, so it's going to be a -4. So cosine is going to be -4 over 5. Any others? 85. Some of these work each problem. Derive the identity. Jeez. Okay. God. They want us to divide x squared plus y squared equals r squared. Divide it all by y squared. Y squared. Squared. And this is also 1 plus cotangent is the same as x squared over y squared. And cosecant is r squared over y squared. Right? So we're almost there. We just need to get this into a condition that we like. So this is the same as x squared over y squared plus y squared over y squared equals r squared over y squared. X squared over y squared plus 1 equals r squared over y squared.
That was a rap right there.
Huh?
That was a rap.
Yeah.
X squared over y squared plus y squared over y squared equals that.
I know.
Dang.
It's musical. Yeah. That one was pretty
Dang.
straightforward. I'm done.
That's it?
That's it. Yeah, I did what they wanted. It's not that difficult. Okay. Any other questions?